So thanks for staying with us this long. The next presentation will be by Clemens on modular and compositional computation. So Clemens, thank you very much for joining us. Looking forward to what you're going to say. And over to you.
Well, first, thank you for having me, and thank you for this workshop. I really enjoyed the last 3 days by now, or 2.5. So, anyways, so I'm going to talk about modular and compositional computation. It might more adequately called modular and compositional learning. And other than a lot of the other talks, this will be somewhat less detailed because I'm trying to, I've been working on this for a while. And I try to wrap my head around many of the involved problems. And what I'm trying to convey here is the thoughts I had and how I basically perceive this entire subject and what do I think are some of the most important problems and how we could potentially tackle them. So I'm basically, it's very straightforward. I'm starting with a quick motivation that at this point, I think we are, like everybody who's on this talk, I suspect will be in agreement on this. So I'm not going to spend too much time on it. Then I'm going to illustrate what I'm going to talk about later with a quick example of the approach that I've been favoring for a while that's called routing. However, I'm trying to just use routing as an example for modular and compositional learning, not necessarily as the way to go. So I'm trying to just keep this general. But this gives me something specific to talk about. Then I'm going to turn over and try to think about what challenges, what problems I encountered, and some of the more principled ways I started thinking about them, and how those can actually be tackled if you really try different approaches than in the empirical observations. And finally, I want to introduce some half-finished work that I eventually really have to sit down and write a paper on about how we may be able to get an angle on these different problems. So just to start, I think motivation is pretty straightforward, right? So we as human beings have this amazing ability to just look at this, admittedly very good, but still ultimately just an instruction. We can compartmentalize it. We can identify every single step in this. We can project it to individual subskills. And once we have assembled one bed in this case, we can very easily translate this ability to continue assembling, for instance, this shelf. Ultimately, because each of those individual skills and components that we use to do the first task kind of reoccur in the second. And this ultimately is about modularity, compartmentalization, and compositionality, because we can decompose the first process. Like if this is so we can compose the assembly of a bed into the sub-skills, and we can reuse them freely whenever we encounter a need for them again. And I think this is honestly my most favorite quote in this entire area. This goes back to 1991 and is by, this is the Mixture of Experts paper, or one of the early Mixture of Experts paper, by Jacobs, Jordan, and Bartow, where they say that suitable design and modular architectures should learn faster than single networks, because similar functions can be learned by the same network of the modular architecture, resulting in the benefits of positive transfer for training, whereas the similar functions can be learned by different networks, thereby avoiding the detrimental effects of negative transfer at training. And I think this quote basically says it all. So this is kind of the underlying goal behind my work, is to have architectures that self-modularize so that we can both specialize, get transfer for cases where we can use transfer, and can avoid negative transfer for when skills are too dissimilar to be learned jointly. So again, because I think we're all in agreement, motivation stays very short. And I want to walk you through the example of routing. I think some of you are already familiar with it. But this is essential for following the next steps. And I'm going to start with the forward pass, if you want, with the inference step of routing. The inference step can roughly be described by, by having two components. So one of them is a set of functions, or a set of in the case of neural networks, individual neural networks, neural network layers, something of the kind, that are at least partially composable. So there are something which I struggled with a lot. There are dimensionality constraints. So you can't just arbitrarily combine those functions. They have to have the same input and output spaces. And you have what I call a router. So you have a composer, a central brain that learns how to compose those. In more detail, say you have an input. The input gets first passed to the router. The router analyzes the input, and based on whatever inference the router does, it selects one of the modules in the set of modules. It then applies the function that this module corresponds to this input, yielding a new activation. This new activation is then basically becomes the new updated internal state, and we repeat this process. So on this new activation, the router makes the next decision and selects maybe a different module, applying it, yielding a new activation and a new activation until some kind of termination criterion is met. Now this termination criterion can be arbitrary. So I tried having architectures where the router could just explicitly select a stop action at which it would terminate. You can just force that there is just a specific number of steps that's always the same, which is particularly important if you route architectures where you have constraints on different layers. So if you route an architecture with heterogeneous layers, because of those dimensionality constraints, you can't just arbitrarily stop in between. You have to actually apply all of those to completion. And at that point, so after you have made or met some stopping criterion, you basically have your output. And your output is then interpreted as either the input to a follow-up layer, or as the output of the entire neural network, or anything of the kind. Now this is, I think, fairly straightforward. Where it becomes more interesting is training, or backward pass, depending on the perspective you take. During training, the thing is that routing, and this is actually an interesting observation that I did not think of before, that we heard in the discussions until this day, is that routing always combines those building blocks by taking each layer and basically just forwarding it into the next. So you have functional composition. Now this functional composition has advantages and disadvantages. Now the first is that I would argue that, so when I designed this the first time, I felt that this kind of functional composition is in many ways the most intuitive. We have an input, and the way that when we think about how we solve problems, we think about a problem, we do a partial solution, we get a partial solution, we do a next step, a next step, a next step. Anyways, so now that we have this output, the question is, how do we train? And we have two components to train. The first component we have to train are the individual modules that we combined. Given that at the point after having your inference, you effectively have a single monolith, you have constructed a monolithic network, all gradients are well defined. So what you can effectively do is you get your output. Based on your output, you compute a loss function. And that loss function that you can then just backpropagate through all of the different module parameters that your network has. Now, this is pretty straightforward. The very interesting, or the more interesting component, arguably, is how do you train the composition? And for the composition, given that we don't have any kind of instructive signal, the only thing that we have is evaluative signal. We only get, as a feedback signal, how good was your composition? And this is natural. This is, at least I felt it, or I still feel, this is naturally a reinforcement learning problem. And because it's naturally a reinforcement learning problem, well, I trained the router with reinforcement learning. Or any other kind of training algorithm that allows me to train hard decision making. So this includes some more recent reparameterization algorithms, such as the Gumbel softmax reparameterization. Two others that I've tried are Rebind, Relax. I'm sure by now, this has already been like 1.5 years. I'm sure there are new algorithms that allow you to do that. But ultimately, the thing is, we have at each individual step in the forward pass, we have some kind of stochastic selection algorithm, be it reinforcement learning or reparameterization. We sample from it, we apply the function, and then at the end, we get an evaluative signal that we can then use to evaluate the decisions we have made that led to this particular composition. And one thing that's just important to notice, I think for again, this is a pretty trivial point for the current audience, is that this is a complete end-to-end process. So we are not doing this on batches. We are not doing this over entire data sets. We're doing this for each sample individually. So you get a sample, you do this entire process, and after you have done the inference steps or the forward step of the sample, you immediately train each individual component. This is important because once just for positioning in the greater research world, if you were to do it on a larger scale, it would very quickly become architecture search. So this is actually, I forgot which one. There was one paper that called these approaches basically generalized one-shot architecture search, because you're doing an architecture search iteratively for individual samples. And this is now the part, so this is until here, it was mostly, and by the way, please interrupt me if anything is unclear. So now that I have explained how routing, this particular approach that I have been favoring for a while, works, I now want to take a step back and think about what is actually involved in this process. And the first here is what I call learning to modularize. Learning to modularize is that as part of this big complex learning dynamics that we have to basically identify what is the responsibility of each individual module that we have. So what function does it encapsulate? These are called learning to, mostly because I'm learning the modules themselves. So what is the exact function that, let's say in this case, F1 describes, including all of its parameters? That in turn means that this, in theory, could be arbitrary hierarchical, because we get a signal here, and the only thing that we do, I mean, then it may not be, sorry, differentiable anymore, but we could, in theory, have, instead of having a simple just parameterized network, we could have, say, a mixture of expert model for each of those individual layers, because ultimately we have no restrictions on how these functions work, with the one exception that each of these functions have to be composable in this particular way. As long as this is maintained, and maybe backpropagable, if you want to use backprop, you can compose them this way. The second thing, again, this is after all of today's discussions, nothing super exciting, is that we are effectively learning to compose, right? So the router and the reinforcement learner is learning how to combine these individual modules and how to compose them in such a way that they're able to actually solve the underlying downstream tasks that we are interested in. But, and this is in a way maybe the most, a very important perspective that I have not seen made explicit anywhere else, is we actually have a third learning component. And we hinted at it several times, but we never made it really explicit. The third learning component is learning to partition. And I think that learning to partition gives us a very interesting perspective of thinking about this problem and how to tackle some of its challenges. So what learning to partition means is that when we when we learn a particular problem, when you learn to solve a particular problem, is that what ultimately happens is, say we have, I mean, in this case, we have 3 to the 3, so we have 27 possible paths. Because we have 27 possible paths, and say we have a data set of a particular kind, what happens here is we need to effectively group samples by their functional similarity. Because only samples that are functionally similar enough, I'm not going to define this formally at this point, is only if they are, so only if they can be handled by the same function effectively, does it make sense to group them. If they are too dissimilar, then grouping them will ultimately not lead to increased performance. So what we're effectively doing here when we do this is we have a very strange latent distance between samples. This distance is how similar can the function be that handles those two samples? So we have pairwise distances. As soon as you have pairwise distances and you do this kind of separation, what you're effectively doing is clustering. So one important perspective for any kind, and I think this actually translates to arbitrary kinds of modular learning. An important perspective on modular learning is how can we basically learn to partition? How can we divide our space of data samples, of components of representation, maybe along a different axes of dimensions? Like this follows up on the discussion we had in the big discussion round with Wendelin. How can you determine which particular dimensions should be handled by the same clustering effect? And this is again very interesting for a different reason. And this is what I asked yesterday in the discussion about emergent communication. I asked Angeliki how multitask learning and communication might be similar in the sense that you need to basically agree on the extent of your concepts. And I think this, under this perspective, what I meant there becomes fairly obvious, because as soon as, let's say we have this particular partitioning here, and say that this partitioning doesn't happen in, like happens in some form of latent space. So I mean, this could be your input space, your input distribution, but this could just as well be some latent space somewhere in the middle of your network. And what we ultimately wish for these algorithms or these models to do is to pick up on a particular kind of preferably human interpretable concept similarity. For these particular examples, like the insect and the giraffe, this would translate to, for instance, recognizing the concept of legs. And that we get in the space of clusters that we learn, we get a thing that kind of reflects the notion of a leg, or the concept of a leg. And even if you, and this is the really interesting thing here, even if you, and this is why I really found the discussion yesterday extremely interesting, is that we can have, or we need, this emergence of specific concepts even when we don't have explicit communication. Because a routing network does not have a notion of explicit communication. It only communicates over the individual gradients, effectively, that each individual piece does to the modules. This is the only way of like very low-level communication that is happening. But even then, the different networks need to agree what is a concept that is worth reusing and recomposing of a different contexts. And again, coming back to my previous point, I think that this learning to partition therefore plays a fundamental role that does not have quite the attention that I think it deserves. And now that we have the three perspectives, right? So we have learning to modularize, we have learning to compose, and we have learning to partition. We can actually, like, just as a thought experiment, try to apply those onto a simple task like before, the one where you have to screw in a screw for your shelf, and try to illustrate where already for such a simple example this becomes tricky. Is that if we try to do this right now with our own, like, already very highly evolved human concepts, of course we could just say, well, you take a screw, you hold the screw, you take the screwdriver, you screw it in. But this is not really a decomposition in atomic skills, because holding the screw, because you have to target the screw the right way, you have to hold the screwdriver, you have to turn the screwdriver, etc. All of these individual skills are somewhat not sharply defined. So we don't exactly know what is involved. We don't exactly know where they begin and where they end. And we don't know when we can recompose them. And this means that, or a different perspective, one that I actually also like quite a bit, a different perspective on this triage is when we think about programs, right? This is a topic that we've been talking about several times, is how can we actually learn programs, or what is the relationship between modularity and programs? Is there any? And I think there is actually a very strong one in the sense that these three problems are three problems that all of us, every time we touch a piece of code, kind of solve implicitly. Because first we need to define what is the exact functional, like the exact functionality that a particular function has to provide that kind of resembles the learning to modularize. We need to decide when do we reuse, when do we need these individual functions throughout our piece of code, which is compositionality, because we reuse, we compose in the structure of our code each individual function every time we use it. And ultimately, and this is again coming back to this particular focus of mine, as partitioning, right? We need to exactly determine the scope of the function, because this function in turn can call other functions, et cetera, et cetera. So what exactly is the scope that we have for a function? And at least I myself find, I find myself to revisit this question when I write something up all the time, because I find, oh, I have this snippet of code that I'm now copying all over. So maybe I take this and create a new function that I can then like more cleanly call from everywhere else. And as I said, these three form a triage. And unfortunately, it's really difficult to look at them in isolation. And because you cannot really look at them in isolation, they lead to a whole lot of problems. And so this is what I now come to, is what I roughly call the challenges of modular learning. And for the challenges of modular learning, there are several, all of which you can explain with this triage. The first one is stability, right? This is why I asked and was quite surprised that Ferren didn't have any problems, because we effectively have three different learning problems. Each of them interacts with the others. If we jointly train this end-to-end, the learning dynamics of the resulting systems are incredibly complex. And just to illustrate, I particularly like the right example. That was a very unsuccessful experiment I ran a while ago, where the model was actually so bad that out of a three-way classification, it found the fourth class that was only there for implementation reasons, meaning that the entire training just goes completely haywire. The second, this is, I don't know whether Lewis is here, but this was first phrased by Lewis, right? Is that you have the problem of module collapse. Modular collapse can roughly be described as follows. Imagine you had a data set and you just know that your data set consists of two linear noisy modes, right? So you have this mode, you have this mode, and what you want to do is basically, because you have now a very powerful model, you want to learn a function that approximates them both reasonably. So this is basically what you want. You have this model that can determine which approximator to choose for which input. And this would be a basically perfect example for this particular two-dimensional example, a perfect solution for this two-dimensional example. But, and now things got tricky, because what if you had a model and you initialized your function approximators like this, right? Each of your different models, you have three, you have yellow, red, and green. And as soon as you initialize them like this, the problem is that for this particular example, both modes of our input distribution are actually have in a greedy selection for minimal loss, which you tend to happen more or less, have the green initialization closest. So what you end up learning is an approximation that just collapses to one individual mode, and you don't really, like you underfit in effect, right? You don't really exploit the structure that you as well as you could. But, and this is another generalization from Lewis's work, is you also have overfitting, right? Like collapse is effectively underfitting, but you also have the other end of the spectrum. Let's now say that, again, for the sake of the argument, we had one pretty noisy linear data set. So we have like our samples with quite a bit of noise, but we ultimately have the assumption, and for whatever reason, we just know that we want effectively a linear approximation. So this, again, is our desired example. But what can very easily happen is that your like composer starts overfitting. Your composer now has, because your composer has the ability to form combinatorial many approximators, it might just as well end up doing so, thereby for each individual subsection of your data, find a separate approximator, thereby vastly overfitting to your data. To make this, to give you like an anecdotal example, is that I trained on a particular data set where I knew that baseline was, again, I think it was through a classification of 33%. I got a trained accuracy of 97 and test accuracy, I think, 45%. So I know that these models can really vastly overfit. I think this is a big danger that we need to be very aware of, that the underfitting or model collapse can, the more flexibility we allow the model, quickly jump over into overfitting, where we, instead of having too little, we have too many different approximation nodes, and thereby don't really generalize to anything interesting. And this quite obviously, when you think through, and I have to thank a reviewer for a paper I submitted a while ago for pointing that out, because I completely missed that, is that you have ultimately an exacerbate the bias variance problem for modular learning. You have this for the simple reason that you already have this for each individual approximator, but now you have combinatorial many individual approximators. So the original bias variance problem that you already have now becomes just like exponentially worse. One last problem of modular learning that I think shouldn't be forgotten and should always be like something that we're aware of is that if we try to add diversity to our modular compositions, so architectural diversity, for instance, say you have an MLP and an RNN or something of the kind, that those will exhibit different learning dynamics. And if you have some kind of actual end-to-end learnable approach, where you don't just, as you do an architecture search, you pick a composition, you train it until convergence, you measure its performance, and you do an update to the composition up front. But if you do this throughout your data set in a more or less online way, you quickly stumble across the problem that in this particular case, even though module 1 would ultimately be the superior one, you only get to that point if you grant it sufficient amount of learning. But to grant it a sufficient amount of learning, you're effectively now in the world of the classical reinforcement learning exploration dilemma, is that you have to explore all the time, thereby losing your chance to exploit the orange curve. Again, another difficult problem, and unfortunately one where I have absolutely no idea how to principally solve this, because these training dynamics are just inherent to the different functions, and there is very little we can do about it. Now that I've talked a little bit about the challenges, I want to come back to some basically high-level empirical observations and how we can tackle this in particular this triage, right? This problem of jointly learning to modularize, to compose, and to partition. And again, as I said, we start with this triage. And when you look at these, and you think about where can I start to address these problems, you very quickly come, or at least I very quickly came to the realization that learning to modularize, learning what the exact functional nature is a very difficult area to start with, right? Because if you already knew what functions you would ultimately need for your composition, you would already have solved most of the problem. So in a realistic scenario, you don't know what the exact functional, what the exact function that you're trying to learn will be, because the function is so heavily intertwined with the two others. So starting here is very difficult. Learning to compose is even worse. Because if we knew to know the correct composition for a particular problem, we need to understand the problem perfectly. We need to understand each individual function perfectly. So there is very, very little room to tackle this triage by learning to compose. So what remains is learning to partition. And I'm sure you already kind of see where I'm going with this. It's because when you think about learning to partition, we quickly realize that multitask learning comes with natural partitions. As soon as you have, if you are in the real full-fledged multitask learning, you have task labels. And those task labels give you a partition, right? They tell you this is one task, this is another task. We don't know how exactly they relate, but we know that this is an externally given partitioning of your sample space that you can now exploit. And so the first big application, or the easiest way to make these modular architectures work is basically by explicitly taking multitask data set, multitask problems, and then letting them run against it. How does this work? In the in my very first work on this, it's that you have, when you have your original domain, you can partition your sample space by your individual tasks. And what you do then is you assign one particular learner, so one composer or one composing agent per task. This turns this entire thing also into a multi-agent problem. Because what you have now is you have, for k tasks, you have k different learners. Each learner has to optimize just for himself which different modules to select, so that the learner can maximize or minimize the loss for its associated samples. Now this is this is both cooperative and competitive, because it may occur that for incompatible learners, they kind of start competing for the real estate of specific modules. On the other hand, for compatible learners, they can happily collaborate and thereby benefit from transfer. And now to show what, sorry, let me check the time. Okay, I'm good. And now the interesting thing is that now the question is, given that we have this particular perspective of tackling this triage, what happens? And to show this is later work. So this is work from last year that was, I think, in NACO, is what happens if you apply this to language? And instead of having some complex model, some RNN or some transformer, what you try doing is to just say, look, we have words. Ultimately, words are words have contextualized meaning, right? Like it's not that you have one word, one meaning. You have many homographs with multiple meanings. You have connotations for words, etc., etc. So the thing is now that the question is, can we actually learn how to disentangle all these latent interpretations of the words by treating them as a multitask problem and by applying a routing network? So what we did is we got the original glove-trained word embeddings, and we apply a couple layers of a routed MLP to each individual word. And then we just sum them. So again, we try to go with a very simple architecture. It's just basically an addition of their representations, however, they're projective representations. So we call the routing SIVO architecture. And what we found is exactly the promise of and this is why I like this assumption so much, it's exactly the promise of modular and compositional learning, is that we were able to find particular transformations that follow our human intuitions. To take this example that comes from the particular data set, is that in this particular data set that we investigated this on, is that the word take is heavily overloaded, right? Because the word take is when you take an opportunity. Take is more of a modal verb that acts on the meaning of opportunity than actually, like in the right case, take the train or take a coin or take my phone in the hand or something of the kind. And so what we found is that for take opportunity, for instance, and take vow, the interpretation of take is ultimately relatively similar. And the path that we actually learned reflected this perfectly. So we have take opportunity applies function block 2, function block 2, function block 3. For take vow, it applied module 2, module 2. So it has a high overlap. It has very similar interpretation. Whereas when we said take the train, the word take had a completely different interpretation. And I think this is exactly the promise of modular and compositional learning, that we can do many of these things at once. We can disentangle latent representations because many of our latent representations are massively overloaded. And we can share interpretation for the benefit of both sample efficiency, of just like functional efficiency in the sense that we don't need as many parameters, etc. And in terms of a friend of mine, he says that as soon as you have high weight sharing, you have this kind of compressed knowledge because you have very high similarity in the interpretation. On the other hand, you have like orthogonalized knowledge if two interpretations are highly dissimilar. Now this leads to a question, right? So is that if we have well-defined, and there are more examples. So I actually did, yesterday night, I did a quick, I have to admit, a very high-level survey of papers that involve this and similar ideas. And I got the feeling that a good third, if not 50%, of all these modular learning approaches actually in one way or another involve multitask learning. Now, this leads to the natural question. If we can do so well, if somebody else has made the effort of actually defining these external task labels, because task labels are in many cases, not in all of them, but for instance, if you look at Cypher 100, which has this multitask interpretation, this depends on some human doing annotations. So we have, again, the problem of labels. So the question now is, can we actually learn this without having the explicit multitask signal? So basically, can we learn to partition without having an external partitioning signal? Again, in the multitask setting, we have the partition given externally. And the first step in this process, and this is again the same NACL paper from 2019, is that we just add an additional network, and we train the network simply to predict the task during runtime. So we instead of doing this end-to-end, we do a separation here. We are saying, look, we just pre-train a network to just predict the task. And then during inference, at least, we can drop the notion of the task altogether. And we are not relying on this task information at inference again, but we're still relying on it during training. So the next question is, now because we were able to get rid of it at least during inference, can we also get rid of this network during training? And so this you could roughly call, can we find Zulu task-like structures in the data? And what we did there is basically the same thing. We said, look, we have a network. Instead of pre-training this network that determines task, we now train this entire thing end-to-end. So this does a couple of interesting things. The first one, so this is a second paper from last year that's, no, it's a tech report at this point, and this is the paper that I actually want to finalize at one point, is that we now have a hierarchical policy view, right? We have first a centralized agent that makes the first decision, which particular task is this? And then we have a couple of the actual routing agents in the lower level that then compose the module, the routing paths for the respective like higher level task that was defined. This is just as a side note. I thought of this when reading through the questions you sent me for the discussion round. I think there is actually not a hard decision between having a centralized controller and having a completely decentralized controller, because this is an example where you kind of blur into another. You do have one centralized controller that then kind of tries to just give as much of the real heavy lifting of the decision making away as possible. Another interesting effect of this is that we now have a hyperparameter where we can define how many parallel partitions do we have. So we can say we have as many as tasks. So we now don't even need during training. We don't need the task labels anymore, but we still need the information of the data set, how many tasks there are. But we could also set this to a smaller number, to a larger number. The options are limitless. And this again limits overfitting because we are kind of not having the full combinatorial explosion anymore, because we can basically say you're just allowed so many fundamental clusterings at a time. I still have a moment, I think. Yeah, I still have a moment. So I actually have 2 more slides for this. I wasn't sure whether I get to this point. Is that the problem with this particular approach that I showed here is that this is still not a solution to some of the challenges I mentioned before. In particular, this tends to collapse or to overfit heavily. So how can you actually stabilize this? And stabilization here because now we have, and this is again following up from our previous discussion where we're shifting around problems until we find a problem that's better defined, as Wendelin put it very nicely. And this is a problem that's better defined because now we have the question, how can we actually regularize this process in a way that can stabilize it? And because we're ultimately clustering, what we can do here is we can just find an additional clustering objective that we add as a regularizer to this partitioning problem. in particular in the way of what I call a routed autoencoder. A routed autoencoder that gets its initial representation and puts it to a very narrow bottleneck. So we're not talking about like a 100-dimensional bottleneck, we're talking about like a 5-dimensional bottleneck or something, and then tries to reconstruct. And this because we're in autoencoding, we're not exactly adding, we're adding an unsupervised objective. So we're not adding an additional objective target that might interfere in the sense that we're trying to optimize for something vastly different. We're just trying to also go for a replication. And by adding a regularizer that is dependent on self-reconstruction, we were able to actually stabilize this end-to-end problem in a way that allows us, honestly, like scarily good performance. Because what this model now can do, and I'm not going to go into the details of these numbers. I don't think they're super important. But what this model now can do is it can actually learn those partitions to exactly reflect its own individual strengths and weaknesses. And it can even do so on very nearly a per sample basis. So if you have, which happens, I wouldn't say it happens often, but which is conceptually very feasible, is that you have in your original data set samples that are labeled as belonging to a particular task, but that are ultimately require a lot of the skills required from a different task, right? Because these task decisions are not hard. So for instance, for Cypher 100 as a different example, there are the first two classes are, I think, aquatic mammals and fish, which naturally are very similar. But we don't, as soon as we impose the multitask distinction, we don't allow the model to make the soft, to say like, oh, I actually, when I'm right now classifying a dolphin, it actually is easier for me to use most of the fish logic than when I'm using when I'm classifying a beaver, for instance. Yes, so that was my talk. Again, thank you for listening, and do you have questions?
So thank you very much, Clemens. There was a lot of interesting topics in there. So thank you. So are there any questions?